So the complement of an event is even denoted by E complement. So if the probability, let's say, of rain today was estimated by the weatherman to be 20%, and this is my event E. So the probability of event E having rain today is 20%, or if you want 0.2. The question is, what is the probability of the complement of the event? In other words, the probability of no rain. What do you think?
80%.
Yes. So it's 1 minus the probability of the event E, which is 1 minus 0.2, which is 0.8, and yes, 80%. So that's the definition of a complement of an event, or E complement. So if an event has a probability, the complement will have 1 minus. Why 1? Because remember, the total probability of the sample space is 1. So 1 minus the probability of rain will give us the probability of E complement. No rain. Very good pick. Thank you. Okay. So the complement of event E is the set of all no. The complement of event E is the probability that event E does not occur. The complement of event E is the set of outcomes which are in the sample space but not in event E. Set of outcomes that are in the sample space. See, this is also true. So the complement of event E is the set of outcomes which are in the sample space but not in the event E, which is correct. That's why we subtracted from 1. Okay, let's see the last one. The complement of event E is the set of all outcomes in the sample space for the experiment. No. So the complement of event E is the probability that event E does not occur. I like that, but I have to tell you that this is true as well. And I can give an example. Is the set of outcomes which are in the sample space but not in event E. So under certain conditions, this is also true. But I do have, I have to show. I have to check a lot of things. But this is true too. This is correct. The complement of event E is the probability that event E does not occur. Ah, yes. So, but it is, as I said, both of them are correct, in my opinion. This happens, and it's correct, as I mentioned before I selected B, that under certain conditions, but I have to see the whole sample space. But under certain conditions, this is correct as well. They are both correct, in my opinion. Good, very good pick. Next question.
Question 4.
Okay, let's take a look at 4. The golf ball is selected at random from a golf bag. If the golf bag contains 8A, 5B, 7C, find the probability that the golf ball is not the type A. Very good example. Let me copy this. Excellent pick. So which problem is this? Number 4. Good. So 8 of A, 5 of B, and 7 of C. And we want to find the probability that it's not A. And we are selecting, we're not selecting, we don't, probability that the golf is not the type. Okay, we're selecting 1. Okay, perfect. So first of all, we always have to start with the total. Can anyone give us the total? So that's the 15 plus 5, right? 20. So out of the total of 20, how many are not A? what is the total number of balls that are not A?
12.
Yes, so it's 7 and 5, right? So that is 12. And this will be the probability for not A. I will simplify. What can I simplify by? I can simplify by 4, right? And I have 3 divided by 5. Or 0.6 or 60%. I don't know what they want. One of these. That the golf is not a type. Okay, so that would be 0.6. Type an integer or decimal rounded to 3 decimal places. So 0.6. Good. Anything else?
17.
You said 15?
17.
17. I'm sorry, I didn't hear. A coin is tossed and a 6-sided die, number 1 through 6, is rolled. Okay. So we have a coin and we also have a die. Find the probability of tossing a head and then rolling a number greater than 1. Oh, interesting. So let me start my page 6. Good. And this is problem 17. Awesome. Good. So we have a coin and a die. Okay, so we want to find the probability of tossing a head and then rolling a number greater than 1. So probability of number greater than 1. A number, okay, perfect. Let me stop sharing. So it says round to 3 decimal places. The probability of tossing a head and then rolling a number greater than 1 is this. Okay. Before we analyze something like this, we have to talk about independent versus dependent events. So what is independent? I'm just going back to the notes that we had. Where is my experiment that we looked at a second ago? This one. So see, selecting a yellow and selecting a blue with replacement, these are completely independent events. But now, if I do not, I eat my yellow M&M and I don't put it back in the bag, those are no longer independent because the probability of blue depended on what I did on the first trial. The first trial, I selected whatever. It's not that important. It is important if it's a blue because that will change here even further. But so this probability depends on that. So they are no longer independent. These two are independent. The probability of blue does not depend on the probability of yellow. So that's the independent situation, and that's the dependent. So for the independent, the probability of A does not affect, and probability of B does not affect, the probability of A does not affect the probability of B. So the probability of A and B is basically the probability of A times the probability of B. For a dependent event, the probability of A and B does not equal the probability of A times the probability of B because they are dependent. So flipping a coin and rolling a die, they're completely independent. So I have the coin here and I have the die here. Who cares? I can flip this coin and I can roll this die. Doesn't matter. The probability of what I get here and the probability of what I get here is not, they're not affected, right? So they want us to find the probability, that's not a good color, the probability of getting heads. How much is that?
50%.
Yes. What is the probability now that the number we get is strictly, so be very careful if it says greater or if it says greater than or equal to. So greater than or equal to is one thing, and just greater than one, and I think that that's, I'm going to share again for a second. Number greater than 1. So not 1. That's what I was emphasizing. So this one says not, this one says not 1. The other one includes 1. Okay. So how many, we already determined that. How many options we have here? Out of the total of 6, and they want us to flip only, to roll the die only once, right? Yeah, it doesn't say, so we assume that it's only once. So not 1, how many?
5.
5. So now finally we want, they're asking us, and, right? Where is it? And. That's another keyword. The keyword is the intersection. It's the same keyword I used in my example, independent and dependent. Find the probability of tossing a head and rolling a number greater than 1. Okay? So then, so that's the probability of heads and a number greater than 1. That is, because they are independent. Because they are independent, this will be 0.5 multiplied by 5/6. Careful how you put in the graphing calculator. You either multiply these two and then divide by 6, or you put parentheses. Be very careful. So 0.5 times 5, I can do that, multiply both the numerators because this is over 1, and then I divide by 6. So 0.5 times 5 divided by 6. And I got 0.41666. So the probability of tossing a head is great. Okay, round to 3 decimal places as needed. Okay, so I have a 0.417. 0.417. Because I had 4166666. Very good question. Thank you for picking that. Good. Next. I wanted to talk a little bit more today about mutually exclusive and non-mutually exclusive events, but I don't want to do it in 3 minutes, 4 minutes that are left, 5 minutes. And I am,
Can you do,
yes.
sorry, can you do question?
I'm sorry, I didn't hear the question, or you didn't say it yet?
I'm sorry. I think my phone swapped over to Wi-Fi. Can you do question 11?
Yes. I'm sorry, I was waiting with you. I couldn't hear it.
No worries. I think that was on my end.
No worries. Two events E and F are if the occurrence of event E in a probability experiment does not affect the probability of event F. We just talked about it. Awesome. What do you think we're going to discover here? when the probability of one event is not affected about by the probability of another event. How do we call those two events?
Independent.
Independent. So this is the situation with the M&Ms when we did put back the yellow one. We didn't eat it. So the probability of event F, which was the blue, was not affected by what happened on the first trial with event E. So these are independent events. Good. So this is what I just showed you, the multiplication rule. The probability of E and F is the probability of E times the probability of F. This is exactly what we had with the die and the coin a second ago. Applies only to which type of events? Anyone? That's it. The word and in probability implies that we use the multiplication rule.
Okay.
Yes. That we just did. Okay, let's choose one more and we can stop. I still have work to do with you in chapter 5.
Usually, can we do 15?
Yes. Good. So this was exactly what we just did, but let's do it. Use the spinner shown. It is equally probable that the very key words. Equally probable. The pointer will land on any of the 6 regions. Fine. So we have 2 pink, we have 3 blue, and 1 gray. If the pointer lands on a borderline, spin again. Okay. If the pointer is spun twice, find the probability that it will land on blue and then purple. Awesome. Are these independent or dependent events? So we want blue and purple. So let me stop for a second. So this will equal P of B times P of purple only for independent events. If they're not independent, I cannot use this formula. Are they independent? Selecting a blue and then a purple. When I select the purple, the probability of the purple, will it depend on the probability of what I got on the previous spin?
No.
No. So they are independent. Can anyone give us the probability of blue? Probability of blue. How many possible blues?
3.
Yes. Out of how many total?
5.
Yes,
Oh,
total of
6.
6. Yep, perfect. How many purple?
2.
2 out of how many total?
6.
Very good. So here's what I like to do. I'm going to stop sharing for a second. 3 and 2 is 6, so this is 1 over 6. So that is 0.333, right? 1 divided by 6. I'm sorry, is 0.16667. I was dividing 20 by 6. I mean 2. So, type an integer or a simplified fraction. In that case, it's going to be 1 divided by 6. 1 divided by 6. Very good. So please finish up the interactive and everything else, 5.1a, 5.1b. What we are going to